So I'm going to officially start the seminar as it's now 12 o'clock. So thank you everybody for coming. It's great to see a nice big audience. And thank you, Adriana, for agreeing to give a seminar. It's wonderful that we can invite you all the way from Brazil. And this is a great thing about virtual seminars. It's also a great opportunity because we've never met. So we're meeting some new people, making new connections, which is really good. So I'm going to do a brief introduction to Adriana, but maybe Adriana, you can expand on this either during or after your talk, because we only just met, but I'm already very excited to make this acquaintance. So Adriana is an assistant professor at University of São Paulo in Brazil. She teaches mineralogy and petrology and lots of other field courses and other undergraduate teaching. So she said that she's been mostly interested in granites for her geological career, but about 3 years ago, she made a switch from the felsic into the mafic world. So she's been more interested in basalts and looking at these big flood basalts that she's going to be talking about today. Really excitingly as well, Adriana is the head of a human rights commission looking at equality in science. So I've asked Adriana if she could perhaps talk about that after her talk, because I know that lots of people here would be interested to hear about that as well. And during her PhD and subsequent research, she spent time in Canada, University of Alberta, and some other institutions. So thank you again for agreeing to give us a seminar and looking forward to hearing about your research.
Okay, I appreciate the invitation. It's quite of a challenge because I haven't spoke English in maybe 2 or 3 years, so please let me know if you can't understand something I say. So I would just share my screen and go straight to it, because then we have time to chat after the talk, right? So yep. Please let me know, Catherine, whether you see my screen, my presentation good?
Yep, that's good.
Yeah. Okay. So as Catherine said, my name is Adriana, but you can call me Adriana. There's no problem. I have a joke I use quite a lot right now. I used to be an acidic and deep person, and now I'm shallow and basic, because as she said, 3 years ago, Brazil saw the birth of its first private funding agency, and as a launching program, they decided to fund young scientists that were asking the big questions of their fields. And they selected maybe 70 young scientists out of 2,000 scientists. And working with granites is gratifying, but I didn't have, a big question about granites, I reckon. So I switched gears to work on the volcanism extinction link. And this is how this project and all the results you're going to see came to be. This work is part of a large team, so it's a group effort. I have students, PhD students, master students. I have foreign scientists working with us as well. So I put my name here, but actually it is a list of maybe 15 people working in this project. So at the end, we can discuss a bit contributions of different people. So I don't know if all of you are aware of the link between mass extinction and volcanism. It's not widely accepted, but it is generally accepted. There are some exceptions, some debates in the literature regarding whether this is the real link or whether volcanism is the cause of mass extinction, the trigger at least for mass extinctions. But what we see in the record for the Phanerozoic, when visible life exploded, we see somehow a connection between the emplacement of continental flood dissolves and increased extinction rates. The most notable of these are probably the Permian Extinction, which is contemporaneous to the Siberian Traps, 352 million years ago. And then there's the famous extinction of the KT limit, which is associated to Deccan, in where is now India, right, that province. But there's an additional trigger for this one, which is the meteorite, as you probably know. Brazil hosts two CFBs, continental flood basalts, these large igneous provinces that are marked here in a G letter and as a J letter. So J is Camp, a Central Atlantic magmatic province, Camp, and the G letter is Permian Extinction. So it formed just before the opening of the Atlantic, and there's a huge difference between Permian Extinction and several other CFBs for that matter, and the ones that caused the extinctions. Although Permian Extinction is very voluminous, it's similar in size and composition to CFBs that caused mass extinctions, believed to cause mass extinctions. Permian Extinction did not cause any disturbances in life. So why is that? Why is that the case? We actually don't know. We have some hypotheses in the literature, and I will go through some of them, but we don't have a definite answer for that lack of causal relationship between a major CFB and a mass extinction event. There are important points when you talk about this link that people might miss sometimes. There is no correlation between the size of the CFB, a continental flood basalt province, and the magnitude of the mass extinction associated. So it can go from no biotic interference at all to extinguish most of the life, as in the case of the Siberian Traps. 90% of ocean life perished, and 70% of the global life perished as well. So extinction seems to be triggered, by single eruptive events. So it's not that extinction is incremental. It's just a large pulse of single eruptive events, and then you trigger a chain of events that trigger, in its turn, trigger the biotic crisis. So you don't have to look for the whole of the province to get an idea about the triggers to mass extinctions. You have to get, what people usually do is they look at the large single eruptive event at the onset of the volcanism and try to establish volatiles that were released through this volcanism. So this cover already the third point. The emblematic examples such as Siberian Traps, the extinction related to Siberian Traps, and Camp show us that the onset of the mass extinction triggering is coincident with the onset of the volcanism. This is to say that the seal phase seems to be more important than the lava field phase, the extrusive phase. Among the volatiles related to volcanism, CO2 and SO2 are the most important ones. There are minor contributions of chlorine and fluorine, or halogens, but recent years, maybe last decade or so, we have been accepting more and more the idea that interaction between lava and bedrock sediments are as important as are the original volatile budget of the lavas. So there are CO2, thermogenic gases, sulfur, and so on, a realm of volatiles that are product of this, you can say, contact metamorphism, or the assimilation of these country rocks by the magmas. So these are the important points. So as I said, Permian is the second largest CFB on Earth. It's huge. There's a counterpart of it. Most of it is in Brazil, the central south part of Brazil, and neighbor countries in South America. But there is a counterpart in Africa, because this is why this is internationally known as Permian Extinction province. It is huge. It is associated not only to the opening of the Atlantic, but it started earlier. It's not a rift, an oceanic rift, right? It is a continental flood basalt. So the rifting started at the continent. There was an aborted rift over here where the magma was in place, and then the opening shift to the east, and then the Atlantic Ocean opened. You see here that Gondwana was about to break up forever, so it is one of the lips that is not associated to Gondwana, right? The Can, which comes 60 5 million years, is also not associated to Gondwana, but the mass extinction triggered by the can, believed to be triggered by the can, has an additional trigger. So it's actually quite inaccurate to compare CFBs that caused mass extinctions with the can. One can never be certain that the meteorite didn't cause much of the harm to life. So at this point, the program for funding young scientists was out, and I asked myself, which question is open that I always wanted to answer? And this is the one. Why is Permian and Deca not believed or not related to a mass extinction event? And I put together very quickly a seed project. We got selected, and this funding agency worked a little different. We had 1 year to prove our self-worth in order to get an extended funding. So we got what today would be $20,000 to expend over this year, and then we got evaluated at the end of this year, and we didn't get extended funding. Spoiler. Okay, so Paraná did not cause mass extinctions. This did not cause biotic crisis, but it did cause environmental changes. And you see, there's not much work, but there's maybe a dozen papers talking about contemporaneous environmental changes that happen worldwide. So you have changing in the oceans, you have what seems to be that adaptation of life to cooler environments, and you have what we now are trying to establish the temporal link better, but we have a noxic oceanic event contemporaneous to the CFB. The problem is that if you don't know the volatile content of the magma, you cannot establish a causal connection between these environmental changes and the Paraná CFB. So this is the lack, the gap we wanted to fill with our research. So the biotic changes, as I said, are mainly related to colder temperatures. So in the Valentinian Hauterivian transition, temperatures drop by 5 degrees. And if you see here, Valentinian Hauterivian, you are 132 million years, 133 million years. And recent dating puts the Permian and Deca province, the onset of the magmatism of the Permian and Deca province at more or less this age. This here is the first paper to come up with the idea that there was a contemporaneous anoxic event in the oceans worldwide that is related, believed to be related to Permian and Deca, at least is contemporaneous to Permian and Deca. And this is recent dating by our research group. Sorry, I didn't manage to get the small cap delta here, so that's why it looks like this. I'm sorry. So this work was published last year in Geology, and the group is our research group actually, and the onset of the magmatism was put to somewhat younger ages. It was believed to be 134 million years, but based on dating of silicic rocks, we pushed this limit to 133 million years. So there's a lot of debate to whether one can use biostratigraphy to calibrate the geological timescale. But the truth is, with these younger magmatism, one cannot attribute the shift in carbon isotopes to the silicic magmatism of the Paraná CFB. There's a problem here with this interpretation. We do not have ages for the seal phase yet. It can be that the seal phase is somewhat older, and then it might be that it matches the shift in and the carbon isotope record. This is scenes of the next chapters. So summarizing the few works that talk about environmental changes at the time of formation of the Paraná CFB, we have increasing atmospheric CO2 without leading to global warming, though. We have evidence that for enhanced weathering, such as higher mica content, let's say, that in oceanic sediments. We have increasing detrital supply to rivers, and this also is an evidence for increased weathering. Plants evolve to adapt to humid climate, and we have an event of deoxygenation of the oceans. The link with global cooling was established or suggested only 2 years ago, so I didn't put it here, but it has it will appear throughout the presentation. So it all points to no global warming. It's not the climate pattern that we observe for CFBs that trigger extinctions, but we do have a climate effect that seems to be mostly associated to cooling, down to temperatures went down 5 degrees contemporaneous to the CFB emplacement. And then we hit a brick wall at this point, because cold snaps are usually attributed to CO2 withdrawn through weathering or to sulfur release, magmatic sulfur release. Ever since Pinatubo explosion in 1991, we know that the apport or the discharge of SO2 gases to the atmosphere can scatter the sunlight and it causes global temperatures to drop by, I don't know, in Pinatubo's case, half of a degree centigrade. In our case, the contemporaneous cold snap was 5 degrees, so it is expressive. So if sulfur was to blame for this cold snap, we have a problem. And this is where we stopped for a while and regrouped and rewrote our research strategy. You can find only 2 information about sulfur in Paraná CFB. One comes from really primitive rocks from the Etandeca, from the African part of the province. So Marx studied sulfur in melting inclusions from picrites. And we have, and this both came out at the same year, right? It's kind of curious, saying that we had over 1,100 ppm sulfur, putting us in the same category as the CFBs related to mass extinctions. And then a few months later came another paper using a really neat approach, but saying that Paraná Etandeca did not carry much sulfur. The lavas didn't have enough sulfur to trigger climate changing, and the authors used this as explanation for Paraná not causing a biotic crisis or mass extinction. So we tried both approaches. We went for melting inclusions, but we had only 1 year, remember? And then we tried this second approach that uses sulfur and clinopyroxene minerals to try to reconcile sulfur contents in equilibrium melts. So this is the paper. It's a really nice paper. The idea is really nice because it's not as time consuming as melting inclusions. It uses regular and widespread clinopyroxene that we can find in any basaltic rocks. So the idea is to analyze sulfur in clinopyroxene and then come up with a partition coefficient for it. So this is what they did. They experimentally determined partition coefficients for sulfur in clinopyroxene and calculated the sulfur content of the magmas. For these, they used graphite capsules, which means that and then I'm going into the specifics here, but this means that oxygen fugacity was really low in these experiments, and that what this tells us, if oxygen fugacity is too low, then you'll have reduced sulfur and not oxidized sulfur. So I should step back a bit. In magma, sulfur occurs only in S2 species, S2- and S+6. So S2 minus is the reduced specimen, and S6 plus is the oxidized species. So when you are using graphite capsules, you are somewhere here. So this is a buffer, yeah, right? Phyllite, magnetite quartz, we use for reference. So 0, you are on top of the buffer. To negative numbers, you are more reduced than this buffer, and positive numbers, you are more oxidized than the buffer. So when you use graphite capsules, you are somewhere down here, which means that you do not have oxidized sulfur available. You only have sulfur S2 minus. And this raises a problem because when you are reduced, when the melt is reduced, what governs controls the solubility of sulfur within the melt is mainly FO2. Sorry, not FO2, iron oxide. So you can do some correlations like this published by Self in Science about decant traps. So when your lavas are, or your melts are sulfide saturated, they follow a linear correlation with iron. And this is not the case when the melts are oxidized, when you have also 6 plus, so sulfur 6 plus in the melt. So this is just to give you an idea about what comes later. So we start here, Marx or Caligari? Should we go for the approach with melt inclusions, or should we try to replicate what Caligari did with parallel samples, broadening the number of samples? We tried both approaches, as I said. These are some images of melt inclusions entrapped both in clinopyroxene and plagioclase. As you can see here, they are not melt inclusions at all. They're not glassy. They have all these features here with iron titanium oxides. They have large clinopyroxene crystals, and then they have a matrix of what seems to be glassy material. But this poses a problem because one cannot safely analyze crystallized melt inclusions for its volatile budget. You have to go through a whole chain of events in order to get these melt inclusions ready for analysis. And we had 1 year, so we just put it aside. Melt inclusions for the silicic varieties are a bit more promising. They look round, they look like proper melt inclusions, but they also have these large apatite crystals. And apatite takes volatiles into its structure. So analyzing this melt over here wouldn't give me any pristine information regarding the original volatile content of these melt inclusions either. So maddeningly is low separation. There's crushing and sieving and separating the CPX crystals and imaging them and reheating them to get rid of these crystals and mounting them. And then the main thing, we have to have a seams or a nano seams to analyze, and we have neither of those. So we just put it aside and tried a different approach. Why not to go for Caligari's approach? It's pretty simple. You analyze CPX, you see how much sulfur is in it, you apply their partition coefficient, and then calculate the sulfur content of the melts in equilibrium with this clinopyroxene. We do not have a seams. Caligari's group used the seams. We as Brazilians used to work on a low budget. We tried to get creative. And for those of you who never saw Azane's spectra, here's one. Spectrum, here's one. So you have energy of the photo beam over here. You have countings, and here these are normalized by a standard. And then each peak that appears over a characteristic energy is related to a specific sulfur valence. So it is a speciation machine. You can define the speciation of a certain element by looking at a window, an energy window that you set it at the machine. And so it is usually used for speciation, but as I said, we try to be creative. There are some works that say that this difference in countings between the pre-edge or the pre-peak zone and the post-peak zone is proportional to concentration. So my students and I synthesized several standards, doped standards, to analyze with designs. We probably did, I don't know, 10 or 12 standards, and went happily to analyze this and try to get a correlation. Well, with the standards, we got a correlation between this difference in energy pre-edge post-edge difference, and we had concentration because we doped them with known amounts of sulfur. And we got a nice correlation, linear correlation, and tried to apply this to CPX. It was epic failure. We got like 3,000 ppm sulfur in CPX. We knew we were way off of the expected values, should be way below 100 ppm. But surprise, surprise, there's, for all the crystals, for all the analyzed crystals, we got only one sharp peak at the energy corresponding to oxidized sulfur, not to reduced sulfur. So sulfur in CPX from Fahrenheit and Deca is S6 plus and not S2 minus. And this has a lot of cool implications. The first one is that we cannot apply Caligaro's partition coefficient to our crystals, because in their case, if you recall, they use graphite capsules, and all the sulfur, most if not all the sulfur, should be equilibrated as S2 minus sulfur, not as S6 plus. At this point, I was really excited. My master's student was really desperate because this was the plan. He wanted to analyze sulfur to apply Caligaro's partition coefficient and to get the sulfur contents of the equilibrium melts, and this was no longer possible. But I was really excited because if you have S6 plus, you have to go all the way to the positive side of the deviation from the buffer, right? The S6 plus curve here just starts going up when you are over, let's say, the buffer, phyllite magnetite quartz, and some 0.2 or 0.5 log units above this buffer, which means that our melts are more oxidized than we previously appreciated. Okay, but we still needed to get the sulfur, and we still didn't have seams or nanoseams. And we tried to get creative again. We have a really good microprobe here at the department, and we pushed it to its limits. We analyzed sulfur 1 hour per spot in CPX. CPX doesn't have the problem of a glass I don't know, migrating volatiles through the structure, or of being damaging the sample due to the electron beam. There's no problem with that. So with CPX at least. So we calibrated the machine. We got the detection limits down to 10 ppm. If you say this is too high, it is. Yeah, SIMS works with the detection limit of 2 ppm. So everything under 10 ppm here have to be disregarded. But what we did see is that this was the previous data set for Fahrenheit and Deca from Caligaro 2014. And we expanded this a little bit, well, I would say a lot, to 64 ppm here. But one can argue that this is an outlier, and it is. So is this from Caligaro work, and this a little less because there's 2 points. So in my student's name, his name is Georgie, is finalizing the manuscript. We are considering 38 ppm as the maximum, and we are seeing this as an outlier. So either way, this puts us in the same level, our CPX in the same level of sulfur content observed for 2 extinction-related provinces, the Can and Can. Pretty cool. Okay, but there's a lot of there are additional implications to that finding. As I said, solubility is increased, right? Because if this diagram here shows this, no, actually it's way ahead. This diagram over here. So sulfur content, when you oxidize melts, melts get more able to carry dissolved sulfur without reaching sulfide saturation. We will discuss this in a bit. So if you are over here, if you have to get mixed valences, you have to have 6+, you have to go all the way to maybe 0.3 above the limit, and then you will start increasing rapidly the amount of sulfur that the magma can carry in a soluble form. So this is pretty cool. But sulfur solubility is different from sulfur content. So we still could not argue for increased sulfur release for the Perrhenite Deca. We could say that the magmas could carry a lot of sulfur because they were a lot of more sulfur than previously appreciated because they have a 6+, but not how much sulfur. And then comes the second part of the outcomes of the results for this project. We came up with a new model. Sulfur in CPX is promising if you use the right partition coefficient. And for this, you have to know the conditionings pretty clear. If Caligara's group is right, and I don't have any reason to believe otherwise, CPX can host both S2 minus and sulfur, reduced sulfur and oxidized sulfur. And we do not know the effects of oxygen fugacity on this partition coefficient. What could be the partition coefficient if we have mixed valence states? These questions have to be answered before we can safely use partition coefficients for sulfur and CPX. An alternative is to use melting inclusions, but too time-consuming, extremely expensive. This is within the scope of this larger project I'm part of, but for this young project, for this seed project, we just abandoned the melting inclusions. And we proposed a new model using calcophile systematics to define how much sulfur there was in this melts. So calcophile is a geochemical classification. Calcophile elements are sulfur-loving elements. So where sulfur goes, these elements go together. So copper, platinum, palladium, and so on. The one that is mostly or usually reported in whole rock chemistry is copper. It is only compatible in sulfides, which means that they are incompatible in silicate melts, in silicate minerals. There are vast data sets in geochemical repositories for all the CFBs, be they related or unrelated to mass extinction. So this is a cartoon explaining the rationale behind the model. So in X, you have a differentiation index. Here is going from right to left. Could be, for instance, magnesium content, magnesium number, and in Y, you have copper content. At the beginning of the magmatic differentiation, copper, which is a strong calcophile element, it has a partition coefficient for sulfides of 1300 and of only half for silicate minerals. So as long as the magma is crystallizing silicate minerals only, copper behaves perfectly or almost perfectly incompatible. At the moment as the magma reaches sulfide saturation, then copper becomes compatible because sulfides start to crystallize, right? So sulfides crystallize and sequester copper from the residual melts. And then you see a drop in copper contents of the residual melts, of the evolved melts after sulfide saturation. With sulfur is a bit different. The initial behavior is pretty much like copper. No one wants sulfur. None of the silicates that are crystallizing, olivine, TPX, OPX, you name it, none of them take sulfur into their structure. So sulfur behaves incompatibly until sulfide saturation is reached. At this point here, as the yellow star in figure B, we say the magma reached the sulfur content at sulfide saturation, SCSS. After this point, instead of behaving like copper and being depleted from the melt, it gets buffered at SCSS. So the evolution of sulfur can be predicted by what we call SCSS models. So this is to bear in mind. If someone, if you have any questions about this, you can ask right now, because this is absolutely necessary to understand the rest of the talk. Okay, so the SCSS. There are several models to calculate how much sulfur a melt can carry without crystallizing sulfur. This is what solubility means. Sulfur is soluble until you reach saturation in sulfides. Then it starts crystallizing sulfides, and the sulfur content of the melt becomes buffered at the SCSS. The problem is there is a realm of SCSS models in the literature. You go all the way from really low contents, below 500 ppm, from models, and coincidentally, the extremes are both from 2002, from models that are really exaggerated and put sulfur contents at 3000 ppm, 3500 ppm. We opted to use intermediate model of Fortin et al. 2015, only because their experiments were performed in conditions related or similar to the emplacement of CFBs. So from 1 GPa to 0 bars in pressure, temperatures in the range of the temperatures we get for the NGL thermometer, and thallitic basalt composition. So we use this purple dashed line over here. And with SCSS, there's an interesting point. If you analyze a whole rock, chances are that this whole rock will be degassed if we are talking about volcanic rocks. So you have your SCSS model. Anything that plots below this line is considered to be degassed, because once sulfide saturation is attained, the melt content, sulfur content, becomes buffered at the SCSS. I keep repeating it because it's really, it took me a while to realize that. So I think it's pretty cool. So this is the calcophile systematics, or copper systematics, if you prefer. You have two phases, and when you look at copper, you have a phase where copper increases with differentiation. So differentiation here also goes to the right. So primitive rocks with higher magnesium have increasing content, copper contents, and then you reach sulfide saturation, and further crystallization leads to an impoverishment in copper from our residual melts. At the point of the kink, in copper trajectory, you reached sulfide saturation. So from this point here, all the points in phase 2 are sulfide saturated, and then you can use SCSS to predict how much sulfur is needed to keep those rocks sulfide saturated. And there's another point, a really cool point. The higher the peak copper content, the more oxidized the melt is. So really low peak copper contents, MORB is a pretty good example of a sulfide saturated series from the onset of crystallization. So you don't see the incompatible behavior of copper before. It is compatible throughout the crystallization series. So here you have a really low copper content, peak copper content, about 100 ppm. The higher you get, the more oxidized the melt is. And then, with summing up, you can calculate sulfur for sulfide saturated sample, as long as you choose rationally your SCSS model. You have P and T estimates. This is quite simple to get. And what we did, we compiled GeoRock repository data for CFBs related and non-related to mass extinction events. So what you see here from C to D, A and B are the pictures I already showed you, and C to D are different CFBs for high titanium basalts in blue color, dark blue color, and low titanium basalts in light blue. The MORB is shown here as this translucent gray. So it is the finest example of a sulfide saturated series from the onset of crystallization. And then you can see here that Paraná and Deccan have these nice triangular shapes, indicating that that copper behaved incompatibly until sulfide saturation was reached. So you have incompatible behavior here, and then you reach sulfide saturation and the copper content decreases. For Siberian and Columbia River CFBs, you see it is a bit different. They reach sulfide saturation earlier in the trajectory. They don't get high peak copper contents. Both of them are around 130 ppm of peak copper content. And the surprise came for Camp. Camp is sulfide saturated throughout the whole of the magmatic series. And this is confirmed here with platinum, which is much more strongly chalcophile than copper. So it is compatible all the way. You do have some outliers here that I can discuss with you during the discussion. So for this part over here, so compiling magnesium contents here and showing them as histograms, we just put the histogram and the point of sulfide saturation as a dashed vertical line here. And then we can assume or assess the proportion of sulfide saturated samples, which in Paraná case is 80% of the repository data, and the Cam case is 60% of the repository data, and Columbia 90%, Camp 100%, and Siberian maybe 76 to 80% are sulfide saturated, which means that for this proportion of the tholeiitic lavas, the CSS can be used to predict sulfur contents of the magmas. And these are showing red lettering over here. For Camp, it's about the same. It's just what this SCSS predicts. When you compare these results of sulfide saturated samples for Camp, Paraná, Deccan, Siberian, and Columbia, these small symbols here are like data from the literature, and the boxes here are data from our model. You see that you get a pretty good match for most cases. Siberian is a complete outlier. These here are data for melt inclusions for alkaline rocks from Siberian Traps. Their alkaline rocks represent 1/3 of the volume, the lava volume, so it's expressive. For the other CFBs, alkaline varieties represent probably, I don't know, in Paraná, less than 5%, right? So for the tholeiitic component, which is the most voluminous one in all the CFBs, you get comparable sulfur results. So this here, this here, this here, this here, right? Camp, there's only the real primitive rocks that surpass 1800 ppm sulfur. For the majority of the rocks you have below 1800 ppm. So the conclusion is the tholeiitic magmatism of the CFBs had comparable sulfur contents. And if they had comparable sulfur contents, it might be that the difference in what triggers and not biotic crisis is CO2 and not sulfur. It also explains, gives us a clue at least, the temperature drop contemporaneous to the Paraná basalts. Different from other CFBs, Paraná basalts intrude aeolian sandstones, so with no potential to increase the CO2 budget of the volatiles, right? Volatile budget. So you have an unimpeded sulfur release without boosting the CO2 release. So the equilibrium between these climate swings, colder and warmer, cannot be seen in Paraná CFB, but can be seen in CFBs that triggered mass extinctions. And this is only the beginning. These 2 papers are ready to go. The second part I showed you, we already submitted and got a desk rejection, so we are repacking everything to send it somewhere else. And this model is for S2 only, right? You can only trigger sulfide crystallization with S2. S6 does not participate in that. We still have S6 as our clinopyroxene suggests. And this puts us on a, sorry, I forgot to tell you something. You can calibrate this copper trend here by twiddling with the FO2 value. And when we did that to the whole of the CFBs, to the whole data sets of the CFBs, Karen and Becan are a bit more oxidized than the other ones. You still have 10% of the sulfur that is S6+. And this has implications for sulfur partitioning. And we can discuss this in a bit more detail during the discussion section. I think, well, I'm almost done. I'm finalizing. This is the last slide. Several of you that are familiar with the subject are probably thinking, well, there is a difference between volcanic emission and what comes from magma-sediment interaction. It might be that you can get a boost in sulfur release from assimilating sulfates from the bedrocks. It is true. And it has been demonstrated, for at least for Siberian, that this is the case. There's a point, though. These here show you that all the provinces reached sulfide saturated conditions. In order to get sulfide saturated, a melt cannot exceed oxygen fugacity more than 2.7 log units above the phyllite magnetite quartz buffer. And this means that the most expressive, the top amount that the magma can assimilate and of sulfate and still be sulfide saturated is limited to 3.5% of assimilation. So the fact that all the provinces are shown to have reached saturated conditions, sulfide saturated conditions, discourages this model for wholesale assimilation of sulfate, bedrock sulfates. If it did occur, it was not a widespread process. Otherwise, it would be recognizable in this large repository data, and we do not see that. We see sulfide saturated conditions being reached, attained in all the CFBs. So be aware that papers claiming that there is the potential for Siberian traps to have assimilated 30% sulfates, bedrock sulfates. This is way off what is allowed for in order to attain sulfide saturated conditions. So it is, for me, it is a localized process. But, and then those that are petrologists are probably asking themselves, could then, if this was the case, if sulfur did got boosted through assimilation, could copper register such assimilation? Yeah, I believe so. If you put S6 in the system, you enhance solubility. If you enhance solubility, it means that the previously crystallized sulfides will be resorbed, and all the budgets they carry, the calcophile budget they carry, will go back to the magmas. So you will see spikes in calcophile trends, as you see here. Let me just take it. As you see here, there are some of the points here in the more evolved basalts that are way off the compatible trajectory here. And I believe this is a reflex of sulfide resorption due to increasing solubility. But you can also increase solubility by increasing temperature and decreasing pressure. Sulfur is a little different from other volatiles in the way that if you decompress, the solubility increases rather than decreasing. Is different, is counterintuitive from what we learned from CO2 or water. So, and this is the last slide, sorry. And I end by sending a message. If you look at this picture again, at this diagram again, you see that the number of CFBs not associated to extinction surpasses by double the number of CFBs associated to mass extinction events. So it's more common that a CFB do not trigger mass extinction events. And what we as scientists are doing, we are looking only at CFBs related to mass extinction events. I don't know if you all have seen this picture over here, but it is usually used to illustrate the survivorship bias. So the Second World War is going on, and the Allies wanted to increase the rate of returning the aircrafts, and they called scientists, they call it engineers, and they kept trying to reinforce the areas that were most hit by bullets. And a statistic said that the information that was not there was more important, because the airplanes that were not returning to the bases were the ones that had the information that was crucial, and they will never get it. So he asked people to reinforce this area over here, and they saw a doubling in the return rates double after that. So we have to be aware of the survivorship bias, because every information we get from a CFB that is related to a mass extinction is human to think that this is a trigger. And only when we start looking at CFBs that do not trigger mass extinction is that we have a clear and complete picture of the CFB extinction link. Okay, this was it. Sorry, it was too long.
No, it was great. Thank you so much. No, it was really good. Maybe if you stop sharing your screen and then we can see everyone on the great. Thank you. That was a really great seminar. It was really interesting, and also hopefully for some of our students, they're linked directly with what they've been learning in petrology recently. So that's hopefully very relevant for them. So do we have any questions? You can put your questions in the chat, or if you want to unmute yourself and ask a question, don't be shy. I was wondering about I know it wasn't really the main thrust of what you've been doing, but the melt inclusions, you were saying, it's really hard to analyze these. Are there any in situ methods, like could you use laser ablation or something like that to analyze them in a cheaper and easier way?
Yes. The problem with our melt inclusions is that they're not glassy. So you have to go through the business of rehomogenizing them in high temperature, and then quenching it very quickly. And then we could use actually our microprobe here. And we are going for the melt inclusions. We just abandoned them for the seed project because we had only 1 year, but we are going for them now. Yeah, it's probably interesting.
Yeah, definitely. And it's fascinating to think about all of those flood basalts that maybe not many people have studied. And if you could make these huge data sets, I guess then you get into the kind of big data sort of.
Yeah.
How do you compare?
I had to learn a bit of statistics. I was not good in statistics at all. You have to learn how to clear the database, because there's a lot of rubbish in there too. So you have to come up with criteria for cleaning up and keeping only what is worth looking at, what is meaningful. It's a lot of work, yeah.
Do we have any questions from anybody? And students, don't be afraid if you are interested and want to ask a question.
Yeah, and if you don't understand something, please do question. Otherwise, I would think you didn't like or didn't understand at all.
No, we did understand. It was good. Thank you. Is there a question?
May I ask a question?
Yes.
Yes. Have you applied your model to the Raj Mahal traps from late Aptian? Have you analyzed this large igneous province?
Well, we had to select. We could repeat this for any CFB we like, actually. But to make a case, we selected 3 of them that are related to mass extinction and 2 that are not, Columbia River and Perna. But it would be interesting to looking at this one. It didn't occur to me to work with large data sets. not large, and well, these are large, but with more data sets, it was maddening the way it is. But I can look at some additional CFPs and see if the pattern stands. I'm not sure, but I really think it does. I really think it's really rare for a basalt not to reach sulfide saturated conditions. It's really rare.
Are there any other questions?
Yes, may I have another question? Because you said that this Columbia River and Parana large explosives were not related to mass extinction, but actually, like in Valanginian and somewhere around middle Miocene, there were small pulses of extinction. They were probably not higher than 15%. So can it be a case that the formation of these large igneous provinces can be a small factor, one of the many factors that it's inducing, like triggering the extinction event, but it's not the main one, and that other factors have to be considered too?
I think you got exactly to the point of our conclusion after this 1 year project. You have to have other factors coming into play. People have suggested that it was continent configuration, the latitude of the magmatism would influence. I'm not convinced of any of those. I really think we should start to look at provinces that are not related to mass extinction events. And when you say 15%, you are absolutely right. But this is not mass extinction, it's extinction. We have several dinosaur species that went absolutely vanished from the record here in South America, contemporaneous to our magnetism. So there is extinction, but it's just not massive. And you have the point. The answer to that, I think, will come when we start analyzing the CFPs not related to mass extinction and playing all the factors together: bedrock composition, latitude, continental configuration, and so on and so forth. I think you're absolutely right.
Great, cool. We have a question which is coming from one of our students, asking for advice about how to get into volcanology. I guess what you're doing is petrology.
Petrology, yeah.
But it is related to volcanology, and it would be, Dean who is here too, Dean would say, you need to do some petrology.
Yes. Well, we are working now in volcanology a bit more. There's I don't know, couple students, PhD, a postdoc, and people from LMU, Munich, are working together with us now. And they are true volcanologists. And you have to get into the physics of things. So lots of thermodynamics, lots of experimentation, but also, and there's where Brazilians come in, lots of field work, field mapping, and knowing the structures. And then you team up with these guys that know a lot about the physics to try to come up with the eruptive styles and check whether this is the case, this is the difference between our CFP and others. Because we do have silicic rocks, but apparently, excuse me, apparently they are effusive, not explosive. And this is really interesting too. I don't know if I answered your question there.
No, I think that was some good advice. I mean, field geology is always the most important, I guess, for those of us who are into the field. But yeah, being able to really understand and describe rocks in the field is so important. So many fields in geology.
Yeah. And geologists are a bit afraid of physics too. I am afraid too. But
I'm afraid of physics.
Yeah, but if you want to be a good volcanologist, I think you have to get the handle of it.
I think we have Phil Benson in our department, who is essentially a geophysicist, but he looks at volcanology. So he would definitely agree with that advice. Great. Do we have any other questions about the talk? I wanted to know a bit more about the work that you've been doing on human rights. So if you would be able to tell us a bit about that I would certainly be very interested. And maybe we can sort of finish off the official questionings now, just because it's 1 o'clock. And if you don't mind staying around for a bit, we could chat about your other work. Okay, so I'm just going to say an official thank you again for a great talk. It was really good, and yeah, hopefully we can do more with the University of São Paulo, because it's been great to meet lots of people from São Paulo now, which is good.
For sure.
Great.
Yeah, the work. If no more questions about petrology, so let's get into the fun stuff. Yeah. Yeah, well, I'm one of a kind. I was one of a kind.